Hello, I'm Taejun Byun, a PhD student from University of Minnesota. I'm going to present our work on a new concept for the assurance of machine learning systems. As machine learning is infiltrating into safety-critical systems, it is becoming a software engineering problem. However, the quality assurance techniques are not catching up fast enough with the disruptive adoption of AI. For example, Zipline flies autonomous drones to deliver medical supplies, and they allegedly spend more than 50% of their time and money in verification and validation. I believe that one possible way of tackling this problem is to adopt proven concepts for autonomous systems. And specifically, I will talk about model-based engineering. Model-driven software engineering is a popular concept that is widely adopted successfully in cyber-physical domain. It argues that we can create various models which capture the abstract representation of the knowledge and activities for a given task and harness this throughout the development lifecycle. It is useful for analysis, verification, testing, assurance, and so on. What if you want to apply this concept for learning tasks? What would it look like? Let's take digit classification as an example. The MNIST dataset comes with 60,000 handwritten digit samples, and if you can introduce human relatable variables for explaining the whole dataset, such as the class label, the size of the digit, the shape, the thickness, and so on, we can possibly explain the whole dataset with this abstract representation. Once this is done, we can measure the adequacy of a test weight against the semantic model that we just constructed, or we can even construct test cases anew from this model that we have, if we have the generated capability. So we ask ourselves this question: can we construct this domain model? And the answer is yes, and it can be done automatically using manifold learning. Manifold learning tries to uncover and analyze the hidden low-dimensional data embedding structure behind the high-dimensional dataset. It relies on model manifold hypothesis, and what that means is that the valid data is actually lying in a topological space that is much smaller than the input space. In this work, we use variation autoencoder for learning the manifold, which is an unsupervised learning technique for obtaining a latent variable generative model. It is composed of two neural networks, a probabilistic encoder and the decoder, joined together by a bottleneck which forces all the information relevant for reconstruction to be compressed. As you can see in the figure, all the digit samples are nicely encoded in this compact two-dimensional space, and different classes are separated naturally and nicely without any supervision. So it finally gives me that compact representation along with the encoder and the decoder, which maps the data to and from this manifold. With this variation autoencoder, the first idea we experimented is the test adequacy measurement. We took the encoder part and the manifold and sliced the manifold into n bins of equal data density per each dimension. For coverage measurement, we check how many of these bins have one or more encoded samples. So we trained a VAE for MNIST and ran the EMNIST dataset as a test suite for evaluation. We first divided the test suite by class and measured the coverage. We then measured the correlation of the coverage obligation to the class label as a representative semantic feature. The result shows that the manifold coverage has a stronger correlation to class labels than neuron coverage or neuron boundary coverage. Another idea that we propose is generating novel fault-finding test cases from the manifold. We use conditional VAE, which learns manifold per class label, so that we can specify the label upfront when generating test cases. Novel test cases can be sampled from this manifold and run on the model under test to find the faults in the model. This framework can quickly generate lots of realistic yet fault-revealing test cases, like shown in this figure. We developed this idea further, and it will be presented in AI Test 2020. So here is a one-slide takeaway. Manifold enables model-based software engineering for learning-enabled systems, and the independence that it provides is valuable for assurance tasks. For concrete instantiation of this idea, we propose a test adequacy measurement and a test case generation technique. The preliminary experiments show that the proposed approaches are viable and effective. I believe that this manifold can be harnessed in other different ways as well, and we are continuing the exploration. Thank you for your time and attention, and please feel free to contact me.